The anatomy of the life of a supercell. Towering to heights of 60,000 feet or more, creating balls of ice the size of grapefruit, tornadoes potentially greater than a mile wide, torrential rain and continuous lightning, supercell thunderstorms are the kings of the Great Plains. When these storms threaten populated areas, it's up to the Storm Prediction Center, National Weather Service, media, storm spotters, and storm chasers to make the public aware.
Oh man, it's huge.
Supercells occur in two general modes, organized and discrete. Organized storms contain multiple supercells embedded into a parent system, each potentially containing heavy rain, strong wind, and hail. These supercells are often outflow dominant, but can sometimes produce tornadoes. The anvil associated with these systems will often trail many miles behind or around the system, producing lightning in the stratiform precipitation region. Organized systems often are preceded by ominous shelf clouds produced by outflow winds. Discrete or semi-discrete mode supercells occur in three varieties. The first, a classic supercell, containing a persistent rotating updraft. Inflow as well as outflow. A core consisting of heavy rain and hail. And an anvil surrounding the storm with light rain. These storms are often characterized by a mesocyclone with boilerplate structure. A low precipitation supercell has little to no rain falling around the updraft or flanking line. The core can still contain moderate rain and large hail, along with light rain and small hail. The surrounding anvil can contain lightning. Storms in this mode can produce spectacular structure, but rarely produce tornadoes. High precipitation supercells updrafts are partially or completely wrapped in precipitation. HP supercell's core consists of very heavy rain and hail, with light precipitation along the outer edges and under the anvil. For a storm to occur, three basic ingredients are needed: moisture, rising and unstable air, and a lifting mechanism. In the northern hemisphere, high pressure pushes air outward and spins clockwise, while low pressure draws air in, spinning counterclockwise. In a typical setup, an area of low pressure enters the plains, drawing in cold and dry air from the west and warm and moist air from the south. We also get lift in the form of a warm front, cold front, dry line, and the low pressure system. Warm air rising is known as convection and is crucial to thunderstorm development. Lift can also be obtained in several other ways. Along fronts where warm air is forced upwards, causing cloud development, and along sharp dry lines, with hot dry air on one side and warm moist air on the other. Orographic lift occurs when an air mass is forced from a lower elevation to a higher elevation as it moves over rising terrain. As the air mass gains altitude, it quickly cools adiabatically. rising the relative humidity to 100%, creating clouds. Lift can also be obtained through differential heating. The sun heats parts of the earth at different rates. This creates different air densities. The propensity for air to rise increases with decreasing density. An unstable air mass is characterized by warm, moist air near the surface and cold, dry air aloft. Air is considered unstable if it continues to rise when given a nudge upward. Forecasters express the amount of instability by CAPE, or convective available potential energy. Often, a layer of warm air forms in the cold air aloft. This is referred to as an elevated mixing layer or capping inversion. If the cap is strong enough, it will force the CAPE to remain below it, limiting storm strength or formation altogether. The cap can be very important as it causes energy to build beneath it. Once the cap is broken, it is gone, and the storm continues to gain strength. As the updraft strengthens, the storm enters the mature stage. A cumulonimbus cloud is born. Cumulonimbus contain a core of large hail and heavy precipitation. The storm will pull in warm, moist inflow from its surrounding environment. As the cumulonimbus reaches the upper levels of the atmosphere, it fans out, forming an anvil. When sinking air is present beneath the anvil, spectacular cloud formations, known as mimotis, can form. A common misconception is mimotis clouds precede severe weather. This isn't always the case, as they often trail many miles behind the storms. Mature supercells often produce dangerous and frequent lightning and intense precipitation cores filled with heavy rain and large hail. Storms often glow green. This indicates the presence of ice. Hail forms inside the turbulent updrafts of thunderstorms. The strong updraft keeps ice airborne. Very cold air aloft causes the ice to grow. Once the hailstone becomes too heavy for the updraft to support, gravity takes over and causes the hail to fall to earth. Sometimes so much hail can fall, the locations resemble a scene from winter. Very large hail can easily be seen on radar and is characterized by a hail spike. This storm showed vertically integrated liquid measuring at 70 decibels relative to Z. Baseball-sized hail was reported from this storm shortly after this radar reading. Slow-moving thunderstorms over already saturated ground can quickly cause floods to develop. Flash floods occur within a few minutes or hours of excessive rainfall. Flash floods can carry vehicles away, lift houses off their foundation, destroy bridges, and tear out trees. Attempting to cross flooded roadways is extremely dangerous and should never be attempted. Rapidly rising water can reach heights of 30 feet or more. Floods are the #1 weather-related killer. 50% of all flood deaths are vehicle-related. 6 inches of moving water can sweep a car away. As thunderstorms encounter wind shear, they can begin to rotate. Wind shear is a change in speed and direction with height in the atmosphere. have this, you end up with a tube of rotating air known as a horizontal vorticity tube. When an updraft encounters a horizontal vorticity tube, it lifts it. This causes the development of a mesocyclone, which is a persistent, rotating updraft. A mesocyclone is a vortex of air within a convective storm, which rises and rotates around a vertical axis. They are most often cyclonic, associated with a localized low-pressure region within a thunderstorm. Their base can be near the surface or elevated in the atmosphere. As a general rule, the surface dew point needs to be 55 degrees Fahrenheit or greater for surface-based storms to occur. A dew point of less than this is unfavorable for thunderstorms to become surface-based because the moist adiabatic lapse rate has a more stable parcel lapse rate at cooler dew points. When dew points at the surface are less than 55 degrees Fahrenheit, storms tend to be elevated. If an elevated storm encounters more favorable dew points, it can transition to a surface-based storm. Surface-based storms are more likely to produce tornadoes due to their base's proximity to the ground. Thunderstorm, rising air is known as an updraft, while falling air is known as a downdraft. Supercells contain both very strong updrafts and very strong downdrafts. The updraft of a supercell is tilted with height, which directs precipitation away from it. The region beneath the updraft in supercells often lacks precipitation, and in such cases is termed a rain-free base. This view of a supercell shows the approximate locations of the mid-level winds at 10 to 20,000 feet, and the upper-level winds at 40 to 60,000 feet. The strong mesocyclone produces an overshooting top above the anvil. Its presence indicates an extremely strong updraft. Warm inflow from the surrounding environment is being pulled into the storm. The forward flank downdraft is the outflow from the rain-cooled air of the storm's downdraft. The rear flank downdraft is air from aloft that is transported down to the surface from colliding with the storm. The flanking line is produced by convergence along an outflow boundary extending from the storm. The wall cloud is located in the updraft region of a supercell. Tornadoes can form at this base. The rotating updraft acts as an obstruction to mid to upper level flow. As high pressure builds upwind of the storm, air begins to sink, forming RFD on the backside of the supercell. RFD can arrive at the surface warmer than surroundings due to adiabatic warming in the absence of precipitation and evaporative cooling. Properties of RFD have an impact to whether or not a tornado forms. The mid-level mesocyclone of intense supercells is strong enough to wrap precipitation around the updraft, creating a characteristic hook echo. The presence of a hook echo does not mean a tornado is occurring or will develop, but signifies a process important in tornadogenesis. Supercell tornadoes occur in the hook area. Velocity products show wind speed and direction. This couplet, captured during the Joplin tornado, shows classic strong rotation. When the values in this couplet are added, The number obtained is the relative wind speed. Wall cloud is a lowering, rotating cloud base where humid, rain-cooled air from the storm's downdraft is drawn into the updraft. Its presence is an indication of a low-level mesocyclone from which a tornado develops. Not all wall clouds produce tornadoes. Ones that do are persistent for 10 to 20 minutes before tornado formation, and also exhibit persistent rotation, as this real-time video shows. Strong inflow winds of at least 35 miles per hour are usually observed near tornadic wall clouds. Often, the base will appear laminar or smooth prior to tornado genesis. The wall cloud will exhibit rapid vertical motion, pulling up small cloud fragments or scud clouds prior to producing a funnel. A funnel cloud is a funnel-shaped cloud of condensed water droplets associated with a rotating column of wind extending from the base of a cloud, but not reaching the surface. A tornado is a violently rotating column of air in contact with the ground and the base of a storm. The United States has the highest number of tornado occurrences, with an average of over 1,000 each year. Tornadoes have been reported in every state in the U.S. Wind speeds in a tornado can exceed 300 miles per hour. For a tornado to develop, a rotating column of air rushing upward must be present. On the backside of the tornado, there needs to be an air mass falling. This air must be at a nearly perfect temperature. If it's too cold, it has the tendency to choke off the thunderstorm, because cold air stabilizes the atmosphere. This air flows out as it encounters the surface, restricting the inflow. When the inflow has a narrower path to go through, it becomes accelerated. Tornadoes come in many varieties. The majority are weaker, lasting just a handful of minutes. While others grow to become violent and capable of remaining on the ground for long durations, lofting debris in their path. Tornadoes are often comprised of multiple vortices. These suction vortices are often violent. Tornadoes can remain stationary or tear across the landscape at speeds in excess of 60 miles per hour. An indicator of violence is a horizontal vortex which snakes outward from the tornado. Cyclic supercells can produce families of tornadoes, as their associated mesocyclones are cut off or occluded by RFD. Consider this radar sequence of a cyclic supercell. Notice the debris ball on the end of the hook, which indicates a strong tornado is lofting debris. The tornado moves southeast along with its parent storm. This is typical of tornado tracks. The rear flank downdraft is now wrapping around the tornado. This causes the tornado to change direction as it separates from the parent rotation within the storm. The RFD has now completely cut off the tornado from warm inflow. The tornado has occluded as it moves into the rain and dissipates. A new mesocyclone is forming and will go on to produce another tornado. These types of supercells can continue to cycle and go on to produce tornado after tornado after tornado. Tornadoes often become wrapped in precipitation, limiting their visibility and compounding an already dangerous situation. To obtain a better view of a rain-wrapped tornado, storm chasers place themselves in a region of the storm some call the bear's cage. This involves placing themselves in the notch of the hook of a supercell. From here, a risky and potentially fatal maneuver called hook slicing is attempted by some chasers, where they drive across the radar hook in an attempt to achieve a dangerously close view of the tornado. This places them in a precarious position should the storm or tornado change direction. On average, about 60 people are killed by tornadoes every year in the United States. Often, observers cannot differentiate between a rain-wrapped tornado and a heavy rain curtain until the tornado is near their location. Many motorists have been killed by driving directly into rain-wrapped tornadoes. When encountering a storm on a day there is a possibility of tornadoes, beware of them being rain-wrapped. As a storm weakens, it becomes outflow dominant. This will cause a tornado to dissipate or rope out. Rotation will cease. The updraft weakens and the storm will drop its precipitation core. The storm is entering its dissipating stage. Outflow dominant storms contain straight-line winds that can still cause significant damage. Furthermore, an outflow boundary from a dying storm can act as a source of lift, possibly igniting new supercells. Outflow boundaries can enhance low-level shear. Some strong tornadoes have been known to utilize outflow boundaries to strengthen. As colder outflow pushes into the warm air ahead of a storm, dramatic shelf clouds can form. These clouds can appear ominous, but tornadoes are unlikely to form in their presence. Outflow winds can pick up large amounts of dust and dirt, causing gustnadoes and haboos. Large-scale, straight-line windstorms, such as derechos, can be as intense as some tornadoes. Supercells can form any time of the day or night, with all hazards possible, including dangerous lightning, large hail, and strong tornadoes. Thank you for watching The Anatomy of the Life of a Supercell.